Ever wonder what truly keeps your lights on and your world connected? Hidden giants of steel and copper never sleep. Each of these giant generators can power a city of hundreds of thousands of people, turning motion into pure electricity. Today, the journey goes deep inside these invisible giants, revealing how they spin raw energy into the lifeblood of modern civilization. In just over a century, generators have grown from workshop curiosities into machines capable of feeding entire national grids.
We tap electricity with a single switch, yet few ever see the immense engines that make that effortless moment possible.
From high-pressure steam to roaring gas and plunging water, every generator begins with one idea: spinning a shaft with incredible force.
At the world's biggest hydro stations, each generator rivals a skyscraper in mass, yet spins with astonishing precision.
To understand how these giants truly work, we must start at their heart, where mechanical power becomes the invisible flow we call electricity.
A single large generator can exceed 10 meters in length and weigh well over 300 tons fully assembled.
In big thermal plants, these shafts spin thousands of times per minute, converting fuel energy into hundreds of megawatts of power.
At its core, a generator is a rotating magnet inside fixed coils, transforming motion into electricity through electromagnetic induction.
The rotor's copper windings carry controlled currents, creating a powerful magnetic field that sweeps through the surrounding stator.
The stator is where electricity is born, as rotating magnetic fields induce high currents in precisely arranged copper windings.
Surrounding each generator is a nervous system of support equipment, controlling magnetic fields, cooling, lubrication, and real-time protection.
High-grade steels.
Specialized factories build these giants piece by piece, using heavy cranes and ultra-precise alignment procedures at every stage.
Just moving a single stator can require dozens of axle lines, special permits, and carefully planned nighttime logistics.
A fleet of large generators in a single station can represent multi-billion-dollar investments and supply gigawatts of capacity to the grid.
Despite high automation, teams of engineers and technicians remain essential, supervising performance, safety, and maintenance schedules around the clock.
Now that the foundations are clear, it is time to watch these generators come alive and synchronize with the grid.
Every start begins with auxiliaries, oil pumps, cooling fans, and control systems must stabilize before the main shaft ever turns.
Fuel or falling water now does its work, spinning the turbine and driving the generator toward operating speed.
Dozens of parameters are tracked in real time, ensuring the generator remains within safe mechanical and electrical limits.
As the rotor's magnetic field energizes, the generator begins producing voltage, ready to be carefully linked to the grid.
The key is synchronization. Frequency, voltage, and phase must match the grid exactly before connection is safe.
At the moment of synchronization, a high voltage breaker closes, locking the generator into the immense power of the grid.
From the generator terminals, energy passes through transformers and races along high-voltage lines toward homes, hospitals, and industries.
Human oversight remains critical, blending field inspections with digital dashboards to keep these massive machines operating safely.
Once synchronized, operators gradually increase load, letting each generator shoulder its share of regional demand with remarkable stability.
Continuous testing and calibration ensure that if anything drifts out of tolerance, the generator can be safely taken offline before damage occurs.
Modern generators rely on advanced digital control systems. Dozens of sensors watch the machine's health, tracking temperature hotspots, rotor balance, and even subtle electromagnetic behaviors. Digital twin software now mirrors each generator in the virtual world, predicting wear and optimizing maintenance long before issues appear. Each generator is tied into regional grid control via redundant communication links.
Sophisticated algorithms adjust generator excitation and output, helping stabilize voltage and frequency when the wider grid is disturbed.
Even in storms and heat waves, these machines adapt to rapid load swings, maintaining a stable backbone for the grid.
Regular overhauls can involve completely removing the rotor, inspecting every critical surface to extend life for decades. Layers of backup power, from batteries to engine-driven sets, Protect critical controls if the main grid supply is interrupted.
New generator designs push efficiency higher, using optimized windings and advanced cooling to squeeze more power from every unit of fuel.
Hydrogen and sophisticated air or water cooling systems allow the largest generators to handle immense currents without overheating. Hydro generators must survive fluctuating water pressures and seasonal extremes while still maintaining tight mechanical tolerances.
During peak hours, entire fleets of generators push toward full output, delivering gigawatts that keep modern life functioning.
Compared to older generations, today's machines deliver more power from the same fuel, with lower emissions and more precise control. Predictive analytics turn generators into self-reporting assets, reducing unplanned downtime and extending the life of critical components.
These spinning giants also act as guardians of stability, supplying inertia and rapid support when the grid is shaken.
Improved generator and plant designs mean fewer resource burned per kilowatt hour, cutting costs and environmental impact.
One large generator can supply hundreds of thousands of homes, or the combined needs of rail networks, hospitals, and critical data hubs.
Many generators run for months at a time between planned outages, their rotors never stopping as long as demand remains.
Over a lifespan measured in decades, reliable high-capacity generators pay for themselves many times over in delivered energy value.
From individual rotors to nationwide networks, these machines are the beating hearts that keep entire grids alive.
Many existing plants are being upgraded, extending the lives of their generators while improving performance and reducing emissions.
These generators underpin heavy industry, transportation, and communication, quietly enabling everything from manufacturing to high-speed internet.
Large generating stations support thousands of jobs directly and indirectly, anchoring regional economies for decades.
New projects aim to integrate even more efficient generators, designed to start faster, ramp quicker, and cooperate with variable renewables. Ongoing research into advanced materials and cooling will push future generators to higher outputs with even greater durability.
Across the planet, nations are expanding and upgrading generating fleets to meet rising demand and improve grid resilience. Far from being obsolete, flexible generators increasingly work alongside renewables, filling gaps and stabilizing power as weather changes.
Understanding these machines means understanding the backbone of modern life, the unseen infrastructure powering our health, knowledge, and connection.
Hundreds of tons of steel spin at thousands of revolutions per minute, quietly sustaining millions of lives every second.
Behind every glowing window and digital signal stand these hidden giants, testaments to human ingenuity.